But well, thanks a lot, everyone in the room for making it today to the last day. Everyone, hello, that are looking online. So yeah, well, and also thank you for the organizers to make this happen. This is my first CuttingEEG conference, and I've really enjoyed it. So I'm going to be talking about the work I've been involved with Wearable MEG since a few years ago now. So this is the outline of the talk. So I'll start talking about the limitations of conventional MEG systems. So well, the aims of why we're doing what we're doing. The emerging technologies available, and I'll try and go through the journey of what's been the OPM MEG journey for us in Nottingham and working with collaborators. I'll show you what the system looks like now and some example applications that we've done with the system, and also talk about the future plans and the recently set up spin-out company that we formed. So to introduce the limitations of conventional MEG systems. So some of you that might not be using MEG, maybe this is the limitations are one of the reasons why I don't use it. So to start with, the magnetic fields that we're trying to measure are really small. They're 1 billion times smaller than the Earth's field. And to put that into perspective with other magnetic fields around us, so not only the Earth's field, but we have a lot of equipment around. So the fields that we're measuring are extremely small. MEG has been referred to as finding a needle in a haystack, and this is why. But we have tools. We have some hardware tools that attenuate external interference, so the systems have to be inside these big magnetically shielded rooms to attenuate the Earth's field and other fields around us. So the current technology is based on superconducting sensors called SQUIDS, and they have really good sensitivity, so about 3 femtotesla. So it's great to measure magnetic fields from the brain. And they come in different shapes and sizes, and the sensors are housed inside this a liquid helium dewar. So to maybe mention some of the characteristics of these sensors. So they're extremely sensitive. They have very high bandwidth, whole head coverage. They've been around for since the 90s. They've been developed. And multi-channel systems are very well characterized now. Some of the limitations, the distance from the scalp to the sensors is actually quite big. Talking in if you're measuring magnetic fields, you want to be as close as possible. So 2 to 4 centimeters is quite big. The sensors are fixed. If there are some reference sensors, these also have to be inside the dewar, and they require cryogenic cooling. So this translates into low signal-to-noise ratio. It's a one-size-fits-all helmet, although they're like adult and baby versions. But that means that the brain-to-sensor distance is even larger in children's and babies. So you also need to keep still, and we've heard from the previous talk, and probably your experience, that is really tricky to scan children, but also movement, adults with movement disorders, and just to scan people in a more naturalistic environment is not really possible with SQUIDS MEG. And also there are high running costs associated with it. So talking about some emerging technologies, I'll just mention a couple, but there's a lot of effort in the field trying to replace some of these limitations. So one of them is a different type of SQUID. It works at slightly higher temperature, high TC SQUID they're called. This is some of the work in Gothenburg, where they are developing these sensors. So this is a 7-channel system. The cryogenics are much smaller, and they can be close, very close to the scalp, so just a millimeter. And then what I will be focusing on is the OPMs. So Optically pumped magnetometers, they don't require cooling, so they work in a completely different principle. And there are so many labs around the world developing, and one of them even, well, very close to here. So again, they come in all shapes and sizes. But it's really been the miniaturization of these sensors that have really excited the MEG field to start to consider that we can use these sensors for MEG. So these are some of the pictures of sensors around the world that have been really miniaturized to allow for OPM MEG. So to compare, to put this into perspective, so sensitivity of OPMs, it ranges quite a lot depending on the size and the technique employed, but have the sensitivity to measure magnetic fields from the brain. The bandwidth is a bit more limited. Maybe I should have changed this. They might get to kilohertz, depending again on the type of sensor. In terms of whole head coverage, we are working on it. So there are about maybe 64 channels at the moment, the systems that are being developed. But a good thing from OPM is that the distance to the scalp is much more reduced. So you're now a few millimeters from the head. There's a flexible arrangement of sensors, so you're not constrained by the dewar. So you can put reference sensors in parts of the body that you want to regress out, or put them somewhere else in the room. And you don't depend on liquid helium. So that brings me to OPM MEG. And this was sort of the vision a few years ago when we were seeing this excitement, these exciting developments from the OPM community, that maybe we could put them on the head and it can look like something similar to an EEG cap at some point. So I'm going to take you through the journey of the developments. We started with some simulations, just so this is what would happen if we bring the SQUID MEG system right on the head. So we obviously will get improvement in sensitivity. So it works at about a 5-fold improvement in signal to noise across the brain. We then acquired the first commercialized sensor from QSpin, and using these subject-specific headcasts, you might recognize this is Gareth Barnes. A bit of a scary-looking mask at the time, but that allowed us to show these improvement in sensitivity with just one sensor. It was about 4 times higher sensitivity than a SQUID. And then we acquired more sensors, and we were able to, instead of being clamped onto the bed, we're able to sit upright and do some scanning. But it's not as easy as it sounds. So what happens when sensors move in a non-zero magnetic field? The sensors might, depending on the type of sensor, but the limited dynamic range might take the sensors out and saturate. So you lose that data whenever there's a big head movement. So my colleague Niall Holmes joined us, and his PhD involved designing these electromagnetic coils to reduce the field even more inside a shielded room. So he designed these biplanar coils that are based on MRI gradient methods. And with this, we are able to reduce the field even more and have then subjects not constrained, even playing a ball game. And we show this. So in here, we show the expected response in the motor area while the subject, well, you might see that that's me wearing that mask, playing a ball game. You can also use these coils dynamically. So this is an example of the fields in UCL. Our colleagues in London, they are very close to the tube line. So every time there's a train passing by, that's because the sensors are magnetometers. They pick up this interference, these field drifts. They're very sensitive to it. But with doing some dynamic nulling with the coils, we can get rid of those artifacts. So after that, we wanted to explore and do different experiments that we haven't been able to do before. So in 2019, Ryan Hill published this in Nature Communications, where he scanned a 2- and a 5-year-old with a modified version of a bike helmet with a few sensors. And after that, we also tried some virtual reality. So given that we can allow now subjects to move, maybe we can immerse them in more realistic environments while being scanned. And this was published by Joel Roberts. And then luckily for us, we acquired smaller sensors that let us then put it on a similar EEG cap. And we did, in combination with EEG, we did concurrent measurements to show similar responses in the EEG and the MEG signal with only 2 sensors at the time. But we also saw that if we have people moving, so trying to replicate what a child might do, we saw that EEG was about 10 times more susceptible to artifacts, maybe muscle artifacts, but also the cap moving. So yeah, this is what the journey's been. This is probably a photo before lockdown. So what is the system now? So you might see here, this is the CTF system that we have in Nottingham. So we were in the CTF room. We've now moved into an OPM dedicated shielded room. So this is made by magnetic shields. You can see the biplanar coils there in the middle picture. And this is a typical noise spectra of the 50-channel system that we have. There are other alternatives for putting the coil system inside the walls. I'll talk about this later. So they're not in the way. So this is a room that's been installed in Surrey in young epilepsy. There's also been some changes to the helmet. So as you can see, these helmets are subject specific. So they were based on a subject's MRI. So then we've explored something more usable. So something that people, especially thinking about kids, that they might be more willing to put on. We've also explored flexible caps. That's probably the best case scenario that you can adapt to any head. But we've sort of decided to stick to generic but 3D printed helmets because that gives us really good accuracy of where the sensors are, where are they pointing. But nevertheless, so we did a study, this was on Ryan Hill, where we compared the performance of a rigid approach, flexible approach, and then compared to the conventional MEG system. And we got really similar results in terms of SNR. So now going through some of the applications that we've done, some experiments with the system. So, well, one of the more exciting things that we were really excited about when we had whole head coverage was can we look at connectivity with OPMs, and so we used this the task data from from this slide. This was a visual motor task, so subjects had to make a finger abduction while looking at this grating that induces gamma responses. So we looked at functional connectivity across the whole brain in the AL atlas in alpha, beta, and gamma. So we scanned 2 subjects multiple times, and then looked at the connectivity patterns that are given by the OPM and the cryogenic. And if I can point you to the middle, so the beta connectivity there, it seems like OPM and cryogenic agree with each other very nicely, and also there might be even some subject differences there between subject 1 and 2, and it seems to be picked up by both systems. So this can be seen a bit closer here. So if we plot the connectivity per subject, so we see OPM in blue and cryogenic in red, they agree really nicely with each other in both subjects. But if now we plot connectivity as per modality, so and subject 1 is in solid line and subject 2 in dashed, there seems like these areas, so the right motor areas, seem to be the difference between subjects, and it's quite nice to see that both the OPM and cryogenic systems see that. So another example that we've been exploring is so different types of paradigms. So things that we couldn't do before in the cryogenic system. If I go back, you can see the video. So that range of movement is a few centimeters. So you can't do that in a conventional MEG. So Ryan Hill's been scanning a few subjects that don't know how to play the ukulele. Obviously, it has to be a non-magnetic ukulele, sadly, but not that difficult to find, luckily for us. And it's really, we see very repeatable localization to the motor cortex while doing this task, even though there are those big head movements, because you need to look down and see what you're playing. And we might be even seeing some differences between left and right hemispheres, perhaps, where the right motor cortex is controlling the left hand that is playing the chords, and the left motor cortex is controlling the right arm or wrist area that's playing the strings. We've also so this is work by Benjamin Witte-Brongo. I hope I said that right. He came to Nottingham and designed this type of sort of BCI where there was a grid. So you see a 3x3 grid on the screen. Each letter or character were flashing at different frequencies and phases, and he was able to get the OPMs pick up. So this requires really high single trial responses to then have subjects just look at the characters of the different grids and trying to type different words. Then a few modifications to the hardware can also help with these new types of paradigms. So now Holmes, our coil guru, he's now, instead of having these intricate wire paths that we had previously, so with these type of coils, you can null the field where the subject is, but it's in the middle of where the coils are. With this new type of coils that are simpler because they're just square coils, but independently controlled, you can, in principle, null different areas of where you are in the room. And this is an example of, where the currents for type of field that is created by this type of coils, it's sort of similar in the square coils approach. So with this, we really like to play ping pong in the lab. So Niall played while he was standing up, sitting down, which is where a kid might be, or on the floor. And really good data was recorded in 3 cases where the null volume is moved depending on whether the person is in the room. And obviously we had to take this further. So we had one person playing ping pong, but now I had to play against my boss. This was obviously during we had to go through a bit of a process in terms of risk assessments, because we were not allowed to be that close in a closed space, and we had to be wearing masks and visors. I don't know if you're able to see it, but nevertheless, so with 2 helmets, 2 sets of sensors, different parts of the room, but inside that, the coil arrangement, we were able to have 2 people interacting. This could be different type of paradigm, but again, getting very so high quality data, even though there are movements, and also you have 2 people in the room, which is really, really exciting. So talking about a bit of future plans. So obviously there's a lot more that can be done. We still, so even though we are reducing the field in the room a lot with these coils, even in a small field, background field of about 1 nanotesla, a little bit of hand motion induces big changes in the field. So we need better ways of reducing the background field. So Molly, she got this published recently, actually, in EuroImage. She's designed a new way of nulling the field in the room, so that it now takes the sensors that are on the subject's head, can map what the field is, and then apply the currents necessary to null the field even more. And what we're expecting to see is a decrease in the low frequency, which is the case. So prior to nulling, so this was an experiment of a subject making movements while looking at this a visual, a 6 Hertz flashing visual stimulus. And you can see that in here is masked, a little bit masked out because of the increase in lower frequencies because of the movement of the head movement. But after doing nulling, that is much more reduced. So, and it's being picked up much better. So as we heard in the previous talk, if we want to look at lower frequencies in infants and other type of experiments where we really want that low frequency, we need better ways of nulling the field. In terms of, so there are also some, there's always constant changes in the field of OPMs. So their next generation of sensors are triaxial. So everything that I've shown you up to now, we have 2 components of the field. So in MEG, normally you're measuring the radial component. OPMs, the ones we've been using from QSpin, they give you also the tangential component. But now next generation can give you a full picture of the vector, the magnetic field vector field. And what is this going to what does this mean? We've done some simulations comparing a radial only system, which is what we've had so far, to a triaxial system. And we've compared what would be the case of an adult and a 4 and a 2-year-old, because it's not a linear change so if you put a sensor on an adult head and on a 2-year-old head, the sensor is going to be much closer to the brain because of the thinner skull. So it's not a linear response. And what we see for a radial-only system, so this is sort of, well, it's the sensitivity, so the coverage that a system gives you is quite homogeneous in an adult, starts to get a bit patchy in 4 and 2-year-olds. So that means you're going to amplify some areas in the brain while losing sensitivity in others. So one way around this could be to actually put the sensors up a little bit further and get a more homogeneous coverage. But with triaxials, you're getting much information of the field. So it sort of smooths out the coverage in small heads. So it's going to be even more critical in babies. And we've had a few triaxials to experiment with this generic helmet made for 4-year-olds. We attempted a 2-year-old and it didn't work at all. So stick to the 4-year-olds, we'll sort those problems at some point. And this was just a simple, so I'm showing here 3 axes of the sensors. But you see in the somatosensory motor areas where the sensors were, this was a simple parental touch paradigm where the parent stroke the kid's hand for a few seconds, and we see a decrease in the beta response with the triaxials that were over the area. Going to something very different. So these OPMs can also give us flexibility to not only look at the brain. Now we can look at the heart, we can look at the spine, we can look at muscles, and we can look at fetal activity as well. So very preliminary results, but we're able to measure fetal heart and maternal heart with sensors. And in fact, very recently in Denmark, Sarang Dalal's group, they seem to have measured some fetal MEG with OPMs, which is really exciting. But obviously, so there are lots of other applications. So we want to explore more this ability of OPMs to be to allow more flexible, more naturalistic environments. So we're starting a project studying Tourette's. People with Tourette's want to go and really bridge that gap between scanning babies to 7-year-olds. Some of the conversations I've had this week is that there is, in MEG, is practically impossible. You have a window that is just not, there's a black hole there that we can't scan kids. And we can also do some more types of hyperscanning, or we've just got a very cool driving simulator, so also look at coherence between brain and muscle activity. Also, I wanted to mention, so due to interest in the OPM MEG field, we set up this spin-out company about a year ago, and we've been established in July 2020, launched really in December, and we've done 2 installations. So the first one is in SickKids in Toronto, in Margot Taylor's lab. That is going to be used for looking at children with autism, which is it is really exciting seeing that this technology is being used in a more clinical setting. Nevertheless, it's not always as easy as it looks. So in Nottingham, I think we're very lucky that we have the lab in the middle of a campus, on the university campus, so there's not much going on around. But putting the system in a hospital in the middle of Toronto with metro lines, elevators, work roads, building works, it was really challenging. So here on the top left, you see the horrible drifts that we see in the lab. This is their MEG lab where they have a CTF system. But the magnetometers are really affected by this due to the limited dynamic range. Nevertheless, using the coils to do some dynamic nulling, we can bring those, sorry, I should have mentioned that. So to put this into perspective, the residual magnetic field is about 25 times worse that we have in Nottingham, and the field stability is about 30 times worse. So quite tricky to, maybe not the best first site to put this in. But with dynamic nulling, we can bring these field drifts down quite dramatically, and then doing some further processing on the data. This has been published by Tim Tierney in London, and correcting for doing a mean field correction, assuming that this interference can be modeled as a spatially homogeneous field. We can regress that, and that brings us to the target noise level of the sensors to then measure brain activity. So we did some comparisons between Nottingham and SickKids. So this is Ryan, who went there on his own to set the whole thing up. He was also scanned multiple times in Nottingham and this visual motor task. So we have the beta response there and the gamma so at the sensor level. In Toronto, despite all the challenges, we were able to also see those responses. And here they're all overlaid one on top of each other, so you can see a bit clearly. And so the second site that we've installed this recently is Young Epilepsy, which is a charity based in Surrey in the UK. I have to say that the background field there is, well, the setting is much more friendly. So we have this room that was already, it was part of a project, an Innovate UK project between Nottingham, UCL and Magnetic Shields. This is the photo I showed at the beginning with the coils that are embedded in the walls. So the residual field is a few nanotesla, and with the coils, you can even get lower than that. And the drifts are very, very small. So it's a great setting to be in. And the exciting thing about this project is that it's going to be used for clinical trials involving children and young people with epilepsy. So they work with Great Ormond Street Hospital in London. So it's really exciting to see that the system is going to be used in this setting. So I think that takes me to the end of the talk. So hope I've shown you that with these OPMs, this new generation of magnetic field sensors have enabled a new type of MEG, maybe a more naturalistic, friendly way of having people in a MEG scanner. They allow for high fidelity data, even when there are some movements. This might open up new opportunities for different types of experiments, so both in the research setting, but also in some clinical applications. And with that, I need to mention all the people involved in all this during all these years, collaborators, all the funders, of course, and all of you for listening. Thank you.
Thank you very much, Elena, for a very thrilling talk, very exciting stuff. So do we have one or two questions before we go to start? Yes, I have one here. Okay. More than one, then. Yes, one here. Yes, vas-y, Nathalie.
Bon, excusez-moi. Hi, I was wondering about the heating, because I read that there is some heating of the system. So what are the specs on this respect?
Yes, that's a really good point. I should have definitely mentioned it. So we're sort of in the opposite. So we're going from cryogenic cooling to the opposite. So these sensors, some of them, so again, different types of sensors operate differently, but the ones we're using, the cell inside has to operate at about 150 degrees. So there's, obviously that's not, and the outer surface of the sensor is more in the 40s, 50 degrees. The way to manage that is, so as probably I should have mentioned it, but with those helmets that, I don't know if you saw in some of the pictures, you can see there probably. So they are they're like lattice sort of structure helmets, so to help with airflow, and we have also some insulation inside, so the sensors are not touching the head, so they're not in direct contact with the head, and there's a little bit of offset from the inner surface of the helmet to the sensor. Also, it's not homogeneous, so there are some parts of the sensor that are hotter than others, and the hottest part is not the one that is closer to the scalp. But that's definitely it is kind of constant worry for us, especially if we go down the line of scanning infants and babies. So yeah, there are some approaches to use some cooling embedded in the helmet, some water cooling, but it is definitely a real challenge. Thank you.
Yes, we have a second question here.
So really cool progress. I'm wondering, are we any closer to being able to use something like this for sleep?
For
Sleep. So having kind of a head on a pillow.
yeah, not at the moment as it's set up. So we have developed this with no sleep in mind. Well, at the moment, so we have this patient support on the helmet. So it's, I mean, something that would be very comfortable to have someone there sleeping, but it's definitely possible. There's nothing really limiting us to design a bed or something more, useful for sleep studies. It's something that we haven't, prioritized at the moment, but I think it's definitely possible.
Okay, we have one last question.
Yeah, thanks. So I was thinking that another limitation of standard MEG is that there's nothing else that you can do during a session recording usually. So I was thinking with OPM, it will be possible, for instance, to record simultaneous MEG and fMRI data, or MEG and during brain stimulation, online brain stimulation.
OPMs in fMRI, I don't think that happening anytime soon. There's some, so there are some OPMs that are actually being used for, I think, to get so with ultra low field MRI to also get the MRI picture, but that's more, I guess, structural. It really depends on what, like, for example, the EEG that we use in combination with the OPMs, it has to be the passive electrode kind of, so you cannot do that with active electrode systems. So it really depends. Obviously, you're quite limited. It has to be very non-magnetic. So whatever you're doing, has to take that into account.
Okay, so I will thank you again.
Thank you.
For a very nice talk. So we're getting in the break now until 11:30. So see you there. Thank you.